Hello folks, today we're talking about linearly independent sets and bases. This is material from 4.3. So as you might realize, we've already talked about this notion of linear independence, but that was in the context of Rn, or R3, R5, where you have vectors with 3 or 5 components, say. But we want to talk about this in the more general context of vector spaces. So let's say that V is a vector space. And so you can think, of course, this includes Rn, but it also includes things like those polynomials of degree at most n, so these abstract vector spaces. So just note that if, let's say, S is a collection of vectors, if this is a collection of vectors in V, right, in that vector space V, then we can still we can consider a linear combination, right? So you can still take, some number times V1 plus some number times V2, ... some number times Vp, and add those all together. We can do that because, remember, each vector in a vector space can be scaled by a number, and that gets you a new vector that then can be added to all the others. Since we have this notion of scaling and addition, this always makes sense. And so here's the definition. The collection S is linearly independent. So, this is a notion that refers to a collection of vectors. This collection of vectors is linearly independent if, well, this is going to look familiar. This is the same example, the same definition we use for the case of Rn. So if the vector equation, right, what I can do now is say, can I make a linear combination of these vectors so that I get 0? And again, we know that there's a 0 vector that lives in a vector space V. If this vector equation has only the trivial solution, meaning, I take C1, 0, C2 equals 0, everything 0. Because obviously if I take everything 0, one of the axioms says actually that if you take 0 times a vector, that always gives you the 0 vector, and so I'm adding up the 0 vector a bunch of times, that gives me the 0 vector. And the collection is linearly dependent if a non-trivial solution exists. Solution exists. And so I want to, this is going to be a very similar story to what we saw in the case of vectors in Rn. And one maybe kind of important fact that should look familiar is that a collection V1 through Vp, well, and let me just, a technical condition, I want V1 to not be the 0 vector. So if you give me a collection of vectors with the first vector, not the 0 vector, this is linearly dependent if and only if some vector Vj, let's say, for j bigger than 1, is a linear combination of the preceding vectors. Okay, so this should look familiar to what, like I said, to what we saw in the case of Rn, that if you have a collection of vectors that's linearly dependent, some vector can be written as a linear combination. In fact, you can take that linear combination, you can take that vector to be a linear combination of the preceding vectors, meaning the ones that come before it in the list. And if you can write a vector as a linear combination of the any collection of vectors, actually, then it's going to be a dependent set. Okay, so again, these are familiar notions from earlier sections, just now in the more general context of vector spaces. And let me give an example in this more general context. So let's take V to be, my favorite kind of example here. Let's take P2, which is polynomials of degree at most 2. And let's take, so let me take vector u to be just 1 vector v to be, let's say, t, and vector w to be 4 minus t. Okay, so these are 4 vectors in this world of polynomials. They have degree at most 2. In fact, they're degree at most 1 here, but they are also polynomials of degree at most 2. And let me show you, so let me prove, or I want you to prove that the collection u, v, w is actually a linearly dependent. It's a linearly dependent set. So what do I have to do? So go back to the definition, right? I want to know, can I write the 0 vector as a non-trivial linear combination of these vectors? Well, this isn't so hard to see, right? So if I took, well, just note, note that if I take 4 times u plus, well, let's say minus v, and then I guess minus w, what do I get? This is 4 times 1, right? U is 1, minus t minus 4 minus t. And what do I get? This is, 0, which is the 0 polynomial, this is the 0 polynomial, if you like, which is the 0 vector. So what I've done here, so I guess the way to think about it is that I've written the 0 vector as a linear combination, right? I've taken 4 minus 1 as the weights, and I get the 0 vector, which is the 0 polynomial here. So that is a dependent set of vectors. Okay, so again, this is the idea for linear dependence and independence in the context of vector spaces. Let me change gears now and give you a new definition. So this is the other main definition of the lecture. Let me just throw out the definition and then we'll talk about some examples. So suppose now H is a subspace of a vector space V. Okay, so think about this again, my cartoon picture here. H is sitting inside the world of V, and so I've got some vectors. They don't actually have to be arrows now; they could be polynomials, but there's some sub collection of the vector space V. Then a collection of vectors, say, let me call it fancy B, which is going to be B1, B2 through B, let's say P. This is a basis for H, okay, that's the new word here, if 2 things happen, okay? So, the idea here is you've taken a collection of vectors, so maybe these are B1 and B2, and the idea is that the idea behind a basis is that these 2 vectors, or however many there are, should somehow, you should be able to build the subspace H out of these vectors, and you should be able to do it in a non-redundant way. So there's kind of 2 things that happen in the definition of basis. First of all, B should be a linearly independent set. And the other one is that H should equal the span of B. Okay, so again, the way I think about this is that the first condition is that there's sort of no redundancy in the collection of vectors. And this is saying that there's kind of enough vectors, so that you can get every other vector as a linear combination. Okay, so a basis for a subspace has these 2 properties. It's an independent set, and it spans the subspace. Okay. So let's go to something we kind of know and love, e.g., what does a basis for Rn look like? Okay, so Rn, right, R3 or whatever n you want to choose. So the basis B should consist of vectors, right, V1, V2, let's say, through Vj. And each vector, right, each vector is in Rn. And what do we want to know? Well, we want to know, right, going back to the definition, it should be linearly independent, and it should span. So if I say that B is linearly independent, this implies that the matrix I get, V1 through Vj, Right? Remember, if I want to, going back to Rn now, if I have a collection of vectors and I want to know if it's linearly independent, that tells me that this, that's the same as saying that this matrix, let me write it like this matrix should have pivots in every column. Right? Remember, pivots in every column is equivalent to saying that the collection is linearly independent. That was our first condition, but we also want B to be a spanning set, right? So to say that B spans Rn implies that this matrix, V1 through Vj, this should have a pivot in every row, right? Okay, well, let's see. So what is this telling us? This is actually putting a lot of constraints on what this should look like. These vectors should have n entries, and there should be a pivot in every column and a pivot in every row. In other words, so what this is implying, the punchline here is that, let's see, so a collection of vectors, let's say V1 through Vn, actually we know, is a basis for Rn if and only if this matrix you get by, putting these guys as columns is an invertible n by n matrix. Okay, so that's an important punchline, important fact that we'll use a lot. So again, this is nice because it ties into things we know and love. It's about pivots in columns and pivots in rows. And again, it also tells you how these invertible matrices make another appearance that, if you give me an invertible matrix, then I get a basis for Rn. So let me just, take an example. If, I don't know, let's take 1, 0, 0, 1, 2, 4, 0, minus 1, 6. Well, so this guy reduces to 1, 0, 0, 1, 2, 0, 0, minus 1, and then I guess, I don't know why I chose this, but this should be, let's see, I want minus 5 halves, so that's 5 halves plus 12 halves, 17 halves, but it's non-zero, I've got 3 pivots. So since this thing reduces, this thing has 3 pivots, this implies that the collection 1, 0, 0, 1, 2, 5, 0, 1, 0, minus 1, 6 is a basis for R3. Okay, you've got 3 entries. Okay, so one other example I want to kind of end with here is that what's the, this was a nice example, but what's an even easier example to, write down that clearly has 3 pivots? Well, if I take, these usual E vectors, this was E1, E2, E3, of course, this, has the matrix corresponding to the identity matrix, which, of course, has 3 pivots, right? Not only does it reduce the identity matrix, it actually is the identity matrix. So this is clearly a basis. This is called the standard basis for R3 in this case. And of course, you have the usual, you can do the same thing for any Rn. Okay, so, and that also tells you why I've been calling these guys the standard basis elements. The EI are called standard basis vectors or elements. Okay, so we've got a good handle on what bases for Rn look like, and we'll continue this discussion with more kind of general settings next time. We'll see you then.